So the cosmic microwave background is the thermal radiation left over from the Big Bang, from the birth of the universe, and it is polarized. So what does that mean? First of all, polarization. So it's thermal radiation. That means it's just like radiation that comes off of a stove burner, or radiation that comes from the sun, or radiation that comes from a radiator. It's electromagnetic radiation made of oscillating electric and magnetic fields. So what does polarization mean there? Polarization just means that the electric fields in the radiation are oscillating more one way than the other. Okay? So it means if the electric field of the radiation is oscillating more that way than that way, the radiation is polarized like this. Perfect thermal radiation is not polarized. It doesn't have any polarization properties, yet the cosmic microwave background is polarized. So this is just this. It's a fundamental process. So how does it get polarized? Where does polarization come from? We are all familiar with it. For example, if sunlight comes and scatters off the atmosphere, it's polarized. But even more commonly, say, if it's scattered off the hood of your car, it's polarized, right? The radiation comes in, and just because of the interaction of the light with the atoms in the hood of your car, the light you see ends up being polarized more with the electric field oscillating like that than like that. That's why polarized sunglasses work. What polarized sunglasses do is they block that component and only let through that component. Okay, so the microwave background, the cosmic microwave background, comes from the birth of the universe, and so there are no hoods of cars in the early universe. So then the question is, so how is it polarized? Where does that polarization come from? So the process through polarization is called Thomson scattering. And first, let's consider that, and this is a process that takes place not at the Big Bang, but later. Not at those very first instances, but later, after the universe has evolved, say, roughly 400,000 years. What happens, and here's how to picture it, is why is it polarized? Well, what is the universe at that time? It's a plasma with electrons, protons. They're coupled by the Coulomb interaction. They're scattering off the photons, and this whole plasma, this primordial photon baryon fluid, baryons just means protons in this case, this primordial photon baryon fluid is moving around. So let's look at one electron in there. Think about one electron. If you have an electron sitting here, and you have radiation from here and here coming at it, and this is hot. Okay, these sides are going to be hot, which means the electric fields are large over here, versus radiation from here and here, where the electric field is cooler. Okay, so the electric fields, so the temperature is cooler, so the electric fields are just smaller in amplitude. That's what it means. So it's hotter here, it's colder here. That's called the quadrupole. Now here's an electron sitting in the middle. Radiation comes in from here. The electron vibrates up and down like this. Radiation comes in top from bottom. The electron vibrates like this, but this isn't as intense. So it vibrates a little less like this than like this. That means when you're looking at me, you see it oscillating more like this, and you say it's polarized. So it takes this special situation of having what's called the quadrupolar distribution, which means hot here, cold here, vice versa, and electrons at a special moment to, and if you have this set up, you get polarized radiation. In the early universe, you have that set up at this period called decoupling, this is a period just as the universe is expanding and cooling, just before it gets cold enough that the electrons can attach themselves to a proton to make hydrogen. Just before then is when this radiation, is when the scattering happens in this way to polarize it. And this is a pretty neat process. You can see that the situation has to be just right. Imagine for a moment you have cold spots up here and hot spots. There's not just radiation that's coming out towards you. What those electrons are doing at the same time is they're taking those hot spots, so this rate polarization now, and it's scattering that into the cold spots. So at the same time as it's making polarized radiation in this direction, it's trying to equalize the temperatures of these other two. So all these processes are going on in the early universe. So now, but let's then say, okay, so there it is. We have this one electron doing this. Where does that special pattern of radiation come from? Where does that quadrupolar pattern come from? Why does it exist? What happens to get this in this particular epoch in the universe is it comes from the motion, the velocity of this primordial plasma. If it were just sitting there, you wouldn't get a quadrupolar pattern. But there's this plasma, this primordial plasma is moving. If you're an electron moving in this plasma, and and this is a little subtle, but if you go into the reference frame of the electron, you see, if the flow has certain characteristics, you see a quadrupolar pattern. So this is neat. All of a sudden, we have a new handle on the universe. Not only can we measure the variation in intensity of the radiation that we see, we can measure the variation in polarization. So whereas the intensity just tells us about just the way gravity is working and where this primordial plasma is, the polarization is telling us about the motion of the plasma. It's like a completely separate way to look at the early universe. We can, in fact, uncover the standard model of cosmology just by looking at the polarization or just by looking at the temperature. Either one of them can give us this information. They give us there's slightly different bits of information, but they sample the early universe slightly differently, but to an excellent approximation, but you can deduce properties separately from them all. So why is that neat? So we can now, we have these two handles on the universe. It's like two separate tests of the standard model, right? We have this built-in check, so we can know we're right. What is happening now, at looking to the future, as we have just now begun to really measure that polarization well. It's been measured fairly, in I think 2003 was the first measurement by the DAISY experiment, and then by the WMAP experiment saw this in enormous detail through the polarization, through its correlation with temperature. And now it's becoming a tool to really measure all the parameters of the standard model. And again, here's why it's special. Imagine that you were looking at the ocean from a high cliff, and you were to just look down on the ocean, you would see waves. And that would be like looking at the early universe. And there's much more to the ocean than that. Those waves are moving, they're interfering, they're crashing. But if you just look at it for a second and you take a snapshot, you can't see that. You have to watch it for a while to see where those waves are going. But now, when we're looking at and that's the momentum of the waves. Now, when we're looking at the early universe, we can look at it in one instant. We see the temperature variations, and through the polarization, we see the velocities. So we get all that information at once without having to wait. So this is exciting. This is the forefront. There are a number of measurements now. At the end of 2014, the Planck satellite will release maps of polarization over the whole sky, all the way around. Before the end of 2014, both the Atacama Cosmology Telescope And the South Pole Telescope will also release large-scale pictures of the polarization. In fact, the Atacama Cosmology Telescope already has. The Polar Bear Telescope, or the Huntran Telescope on the Polar Bear experiment, has just recently released pictures of the polarization. And the BICEP experiment at the South Pole has recently released pictures of the polarization. So these experiments are all maturing now, and in the near-term future, we'll have this brand new picture of the universe through its polarization properties as opposed to through its just temperature properties.
I'm Scott Hannes. I'm the Director of User Instrumentation and Facilities here at the National High Magnetic Field Lab, and I work with all the users who come and actually run an experiment in here in the magnet cells where the actual work is done. The reason people come here to the Magnet Lab is not just the magnetic fields, but the facilities we have to put in them, the sample environment we call it, which may be a combination of temperature or pressure or types of measurements. We have a cryostat that extends in a long narrow tube into the narrow bore of the magnet. They allow us to go down to a few tenths of a degree above absolute zero. We also have furnaces. We can go up to several hundred degrees above room temperature. So we have a wide range of sample environments that we provide to the experimenter.
What do they put in the magnet?
Almost anything. We've measured the strength of epoxies, we've measured steels, and looking at changes with heat. We've looked at grain boundary growth in zinc. We've looked at semiconductors like in your electronic circuit, things that are superconductors. The experiments usually attach on a long stick. To be technical, we call them probes. And on there we put whatever we need to do to manipulate the sample, to change its angle in the magnetic field, to change its temperature. We put a little heater down there, thermometers. We measure their length as it changes in magnetic field down to basically atomic scale changes. And this whole thing goes in a vacuum tube that we put on top of our cryostat, and we lower it down. Then the whole end of the cryostat, all these little wires coming out that bring our signals, are connected to a rack of instrumentation. Various amplifiers and voltmeters and current meters. The usual way of taking data is fix the temperature and change the magnetic field, taking data of what changes in their sample as the magnetic field changes, or sit at a fixed magnetic field, ramp the temperature over a region of interest where they see a certain type of phenomena. The equipment rack is connected to a computer which will record this all, which they can analyze as they look at the data make decisions on how to change the temperature, what temperature to do next. So it's very interactive. This isn't something where they push a button and the data all flows out and it's all pre-planned. The data they then take home, they write their paper and publish it, and hopefully give us some credit for providing this facility for them to use.
How much space do you have in there for the experiment?
The bores of these magnets, they're 32 millimeters. Well, that's a fairly good 1.25" type distance, but then we have to put the cryostat in there, and we have to put insulation to insulate, and I may need to put a cell that compresses the sample. And if I need to rotate the whole thing, I may be down to fractions of a millimeter for this sample. Depending on what we do, the samples can be very, very tiny, but we are very clever at designing experiments that can use the smallest chunk of sample that we can fit in there in the sample environment we need to.
Hidden Magnetic Portals Around Earth, presented by Science at NASA. A favorite theme of science fiction is the portal, an extraordinary opening in space or time that connects travelers to distant realms. A good portal is a shortcut, a guide, a door into the unknown, if only they actually existed. It turns out that they do, sort of. And a NASA-funded researcher at the University of Iowa has figured out how to find them. We call them X-points, or electron diffusion regions, explains plasma physicist Jack Scudder of the University of Iowa. They're places where the magnetic field of Earth connects to the magnetic field of the Sun, creating an uninterrupted path leading from our own planet to the Sun's atmosphere 93 million miles away. Observations by NASA's Themis spacecraft and Europe's cluster probes suggest that these magnetic portals open and close dozens of times each day. They're typically located a few tens of thousands of kilometers from Earth, where the geomagnetic field meets the onrushing solar wind. Most portals are small and short-lived. Others are yawning, vast, and sustained. Energetic particles can flow through the openings, heating Earth's upper atmosphere, sparking geomagnetic storms, and igniting bright polar auroras. NASA is planning a mission called MMS, short for Magnetospheric Multiscale Mission, due to launch in 2014 to study the phenomenon. Bristling with energetic particle detectors and magnetic sensors, the 4 spacecraft of MMS will spread out in Earth's magnetosphere and surround the portals to observe how they work. Just one problem: finding them. Magnetic portals are invisible, unstable, and elusive. They open and close without warning, and there are no signposts to guide us in, notes Scudder. Actually, there are signposts, and Scudder has found them. Portals form via the process of magnetic reconnection. Mingling lines of magnetic force from the Sun and Earth crisscross and join to create the openings. X-points are where the crisscross takes place. The sudden joining of magnetic fields can propel jets of charged particles from the X-point, creating an electron diffusion region. To learn how to pinpoint these events, Scudder looked at data from a space probe that orbited Earth more than 10 years ago. In the late 1990s, NASA's polar spacecraft spent years in Earth's magnetosphere, explains Scudder, and it encountered many X-points during its mission. Because Polar carried sensors similar to those of MMS, Scudder decided to see how an X-point looked to Polar. Using Polar data, we have found 5 simple combinations of magnetic field and energetic particle measurements that tell us when we've come across an X-point or an electron diffusion region. A single spacecraft, properly instrumented, can make these measurements. This means that a single member of the MMS constellation, using the diagnostics, can find a portal and alert other members of the constellation. Mission planners long thought that MMS might have to spend a year or so learning to find portals before it could study them. Scudder's work shortcuts the process, allowing MMS to get to work without delay. It's a shortcut worthy of the best portals of fiction, only this time the portals are real. And with the new signposts, we know how to find them. For a portal to more NASA science news, visit science.nasa.gov.